Hello, everyone. First of all, thank you very much for the organization of the meeting, and I'm very happy and proud to be here in Houston. So I think most of you don't know me because I'm a first-year PhD student. So I work on the cryomagmatic activity on Europa, and I'm supervised by Hélène Massol and Frédéric Schmidt for the Universite of Paris-Sud. So my thesis work is based on the observation of this kind of smooth, smooth lobate layers. And Miyamoto shown that this feature could result from the effusion of liquid water or brines at Europa's surface. And so in this work, I propose a mechanism in order to predict the timescale of the eruptive events and the deposit volume they produce on the surface. So first of all, Manga shown that water directly rising from the internal ocean is a very unlikely mechanism because of the really high pressure it requires. So I made the assumption of the presence of subsurface reservoirs present in the ice crust. For example, they could be produced by local tidal heating in the crust. Manga shown that the dye propagation is possible in the elastic conductive layer. So I limited my study to the 10 first kilometers of the ice shell. And I also made the assumption that the dye propagation is instantaneous in this shell. Here is the model I use in my study. So at the first stage, I consider a totally liquid water pocket in the ice shell. That is at isostatic pressure. And as suggested by Fagans, this pocket will freeze, and this will induce a pressurization in the reservoir. When this pressurization is high enough, we reach the ice tensile strength on the walls, and so the pocket can break. Once the chamber is open, the liquid flows at the surface, and when enough liquid is emitted at the surface, the eruption ends because the pressure in the chamber equals the pressure of the liquid column into the dike. So I presented you the very general model. So now we can look at the necessary time in order to reach the ice critical tensile strength on the walls. So this critical strength is associated to a critical thickness of frozen cryomagma. And by solving the Stefan problem, we can deduce the necessary time in order to freeze this critical layer. So once the chamber is open, the liquid flow at the surface is driven by the overpressure in the chamber. And here is the expression of the flow, the velocity of the flow in the dike. As you can see here, once the chamber is open, the total pressure in the chamber decreases during the eruption, and the eruption ends when the total pressure in the chamber equals the pressure of the water column into the dike. So in this study, I vary many parameters. So for example, I studied the influence of the volume and the radius of the chamber. I also study the influence of the chamber depth under the surface. And I vary the liquid and ices composition by varying their density. I fixed some other parameters that are the compressibility, viscosity, and thermal diffusivity. So I took the pure liquid water values and the ice water for the thermal diffusivity. I also fixed the chamber geometry as spherical. So now that I presented you the different steps of my model, here are the results I obtained considering the freezing time scale of the liquid pocket. So on this first graph, you can see the critical cryomagma fraction we need to freeze in order to break the chamber. So for pure liquid water and for a mixture of water and salts. And for my briny cryomagma, I took the mixture suggested by Corgel. And so we can see that the critical cryomagma fraction is 2 times higher for the briny cryomagma, and this is because this fraction depends on the density contrast between the liquid and the corresponding ice. And this contrast is 2 times higher for the pure water. So we need to freeze less pure water in order to begin the eruption. On the second graph, you can see the time required in order to freeze this critical fraction of cryomagma, depending on 2 parameters that are the chamber depth under the surface and the chamber volume. There's time vary a lot with the composition. So finally, we can see that for a briny cryomagma pocket, we need approximately 1 month to 300 years in order to freeze the chamber. But for pure water, it ranges from few days to 50 years. And so here are the results for the eruption duration and the total emitted volume at the surface at the end of one cryovolcanic event. So I also plotted it depending on the chamber depth and volume. And this time the difference between the results for a briny or pure cryomagma are not that much different. They only vary a few %. And finally, for the eruption duration lasts from few minutes to few tenths of hours. And the emitted volume at the surface ranges from 0.1 to 1% of the chamber, which represents small volumes, always under 1 cubic kilometer. So to quickly sum up this model, the Cryomagma Ascent is possible thanks to the freezing of the pocket. The freezing timescale ranges from few days to 300 years, and the frozen cryomagma fraction corresponding ranges from 1 to 25% of the chamber. Once the eruption begins, it lasts from a few minutes to a few tenths of hours, and the corresponding emitted volume at the surface is always under 1% of the chamber. So we can compare the freezing timescale of the chamber with 2 other timescale relevance for Europa. So first, we can say that the eruption is possible before the water percolation that is computed around 1 to 100 kiloyears by Kalusova. And secondly, the Maxwell time of the ice is around 300 years. So the hypothesis of elastic ice is valid for most of our results. And finally, the time delay until the dike propagation occurs until the beginning of the pressurization of the chamber is very small, around 1 second. So we take the approximation that is instantaneous. So the last thing we wanted to do is to compare these results with the observation of the surface. So I took the approximate area of the structure and our volume ranges, and so I obtained that this feature should have a thickness between 1 millimeter to 100 meter. So it seems plausible, and it's in agreement with the volume for these features computed by head. And our perspective and future work is to conduct this exercise with more accuracy by conducting a stereoscopic study. And that's all. Thank you for your attention.
In calculating the Maxwell time, are you saying that the response of the wall rock around the pressurized chamber does not accommodate any freezing on timescales less than that? Exactly what were you getting at with the Maxwell time?
Yeah, okay. So with the Maxwell time, I only compute that the ice is in the elastic regime, so we can take the elastic response for the ice tensile strength. But we also have compute that for the pressurization of the chamber, if we take the viscous response of the ice, we obtain a volume variation that is approximately 10 to -4 of the chamber volume. And so the cryomagma volume that we freeze is approximately 1% of the chamber. So for the first approximation, we take the approximation that the chamber does not expand. We neglect it.
Okay, that's good, because one of the things that's always kind of haunted me after that paper that I did was that I was completely neglected to even explore any kind of response of the country rock or country ice. But I'm glad you've done it better.
Yeah, first approximation isn't okay.
Okay.
Yeah.
So you had a graph, I think, where you showed different volumes of I think it was volumes of the chamber, if I was reading that correctly. So it was a range. So you have a
can you speak sorry.
Sorry. So I think you had a plot where you showed kind of on the horizontal axis volumes of chamber volume. There. Okay. So this is a range of volume.
Yeah.
I'm sorry?
Yeah, you mean the radius of the...
Yeah, that's what I'm getting at.
Yeah, okay. So the biggest chamber is approximately 1 kilometer in radius, and the smallest one 100 meters, if I remember.
100.